Look at matrix multiplication from section 5.2. One of the things we'll always see is when we're doing this product of a matrix, we take the one on the left, the first matrix, we take the first row times the first column of the second matrix. So this is our left matrix, this is our right matrix. We're going to see multiplication is, the order is important as we do multiplications with a matrix. So one example is we maybe online, we're going to download 3 movies and they cost $10 each. We're going to buy 5 albums from Choplin at $8 each. And we could calculate the total spent by taking price times quantity for each items and then added them. So something like this, the 3 albums at $10 each, the 3 movies at $10 each, the 5 albums at $8 each. So that's $30 plus $40 gives us $70. We're going to see how this works out to be matrix multiplication. There's always a multiplication part and an addition part as well. So first we'll put them prices into a row matrix. They call it a vector, that's fine. We could also call it a matrix. Right? 10 and 8, where 10 is the cost of the movies, 8 is the cost of the albums. We also will have a price matrix. That is our price matrix. We will use a column matrix to list the quantities. And so we take the price matrix times the quantity matrix, and how that works is we take the first item from the first row and we multiply it by the first row of the first column, right? And then we take the second column from the first row of the first one times the second row in the first column of the second one. So 10 times 3, 8 times 5, and then we add that result together. And we're going to do this on several examples, so you're going to kind of see how this works. And it gets a little bit more complex as we get more rows and more columns going along. But one of the things you will always notice, if we look at the dimensions of these matrices, the first matrix has a dimension of 1 row by 2 columns, and we're multiplying that by a matrix that has 2 rows by 1 column. And you'll notice that whenever we are able to multiply 2 matrices, this middle dimension between the left and the right always has to be the same, because there has to be enough items to match up, to pair up equal numbers. What will happen is that these sort of, in a way, cancel out through the multiplication process, and the new resultant matrix will be the dimensions on the far sides, in this case a 1 by 1 matrix. Okay, so that's kind of what this all is talking about. So we're going from left to right, and corresponding entries we're multiplying, and then we add those results together. That's called the product of AB, which are 2 matrices. And we go through and we notice that the middle dimension is much math. You can read these, it gets a little confusing to myself, but if I think of just the middle dimensions need to match, then we will see that always works out. Okay, and let's go through and look at another example. Here's a single row, a single column, but we've got 3 items in each. Again, to do this multiplication, we're going to take 2 times 2, right? That's there, we get an answer. We're going to take 4 times 10, get an answer. We're going to take 1 times -1, we get an answer, and then we add these three together and end up with 43. Notice this was a one row by three columns. The second matrix was a 3 rows by one column. So when we multiply, the middle term canceled out, and we were left with a 1 by 1 matrix, which is just the answer of 43. Let's take another look, a look at another example. Here is a 1 by 2 and a 2 by 1. We've done this example, the size at least. So when we multiply these out, we're going to end up with a 1 by 1 matrix. So again, we will take 2 times negative 3, which will give us negative 6. We take 1 by 1, which is 1, and we add those two together. So our final answer is going to be negative 5. So the row is on the left and the column on the right. If the dimensions are correct, we can do it another way, but that's how we're going to stick with. The row size has to match the column size, right? The middle dimension has to match the 1 by 3 and the 3 by 1. So these middle dimensions had to match, such that something like this, which is a 1 by 3, and this second is a 2 by 1, these do not match. We cannot multiply. It's not defined. Okay. Something that cannot be done. So let's take a look at how we might do this with a larger matrix, more columns going. So here's our first row, right? This is a 1 by 4. This matrix over here has 4 rows by 3, so it's a 4 by 3. And so when we multiply these two together, we can do it because their middle terms are the same. And we're going to end up with a matrix that is 1 by 3. 1 row, 3 columns. Backwards. 1 by 3. 1 row, but 3 columns. So the first time we're going to, and I've got the answer here, but you take 2 times 1, 0 times 1, negative 1 times 0, 3 times negative 3. So the row times the column times 2 is 2. 0 times 1 is 0. Negative 1 times 0 is 0. And 3 times negative 3 is negative 9. Add those together, and we get negative 7. That's what that one is there. To get column 2, it's nice to be able to kind of get these out of the way. And you just see it's kind of, it gets more and more complicated, right? Go with this time. So 2 times this one, 0 times 6, negative 6, negative 1 times 5, and 3 times 8. So that's going to give us 2, 0, negative 1 times 5, negative 5, and 3 times 8 is 24. We add these together, and we're going to get 26 minus 5 should give us a positive 21, which is what they've gotten here. And finally, again, in this multiplication, let's go with red. We're going to take this last column here, this row 1 times column 3, 2 times negative 8, negative 16, 0 times 0, 0, negative 1 times 2, negative 2, and then 3 times 1, which is 3. Add all of these together, that's negative 18. This is going to be negative 15, which is that number right there. So the biggest part of this is finding a way to organize your scratch work in a way that you can kind of see what's going on. But you can see if we had a couple rows going on and we had these columns, it's going to be even more complicated. So we're going to push on to something like that. Okay. We've done a 2 by 2 to a 2 by 2. We haven't done it yet, but this is a 2 by 2. We're multiplying by a 2 by 2. Two middle terms are the same. They're going to cancel, so we're ending up with a 2 by 2. So row 1 times column 1. So 1 times 3, negative 1 times 5. So that's 3 and negative 5. And we add those together, and that's going to be negative 2. Now that's going to be the first row, first column. For the second row, first column, we're going to take 0 times 3 and 2 times 5. So that's second row, first column. First column. Get the second column, we will take first row times the second column, and that's going to give us the first row, second column. Times 0 is 0. Negative 1 times negative 1 is positive 1. That gives us 1. And then we take the second row times the second column. 0 times 0, 0. And then 2 times negative 1 is negative 2. We add those together, we get negative 2. And that's that value there. Multiplying matrices. Rows on the left, columns on the right. Always. Okay. We can do this here. Again, row times column. So this is a, remember, this is a 2 by 1, and this is a 1 by 2. So first of all, we're going to come here. The middle terms will cancel. We're going to end up with a 2 by 2 matrix. Answer here, 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 and here. So we take row 1 times column 1. Negative 3 times 2 is negative 6. We're going to take row 2 times column 1. 1 times 2 is 2. Next, we're going to take row 1 times column 2. 3 times negative 1 is negative 3. And notice in this case there's no adding because there's just a single multiplication. And then the last one is going to be 1 times 1, which is 1. And so there's our answer. By 2 matrix. This one is 2 rows by 4 columns. The second matrix is 4 rows by 3 columns. When we multiply, the middle dimension will disappear, and we'll be left with the matrix. Our answer matrix will be a 2 by 3. So 2 rows, 3 columns. 1, 2, 3. And let's just kind of go through here. So, and you can see we're going to get the 3 columns and the 2 rows. So we got 2 times 1. Let's see how I organize this. 2 times 1 is 2. 0 times 1 is 0. Negative 1 times 0 is 0. And then 3 times negative 2 is negative 6. I need to add all these together. I get negative 4. That's what goes here in the first row. Get the second row, first column. We take this row times the first column. So we do a 1 times 1, which is 1. Negative 1 times 1, which is negative 1. 2 times 0, which is 0. Negative 2 times negative 2, which is positive 4. That's 5 minus 1 is 4. So that's what goes here. Okay. So let's clear out some of this. Okay. So now we're going to take the first row times the second column. That's going to be the item right here. 2 times 1 is 2. 0 times 0 is 0. Negative 1 times 5 is negative 5. And 3 times 8 is 24. We add all that together. It's 26 minus 5 is 21. Get the next item, the second row of the second column. Take the second row times the second column. And so 1 times 1 is 1. Negative 1 times 0 is 0. 2 times 5 is 10. Negative 2 times 8 is negative 16. Let's add these together. This is 11. Negative 16 is going to give us negative 5. If we did that all right. And you can see it's very easy to make a mistake here. You're doing a lot of things visually because it's just hard to lay everything out. Find enough space for everything. And even I find after you're all done, it's hard to sometimes come back if you made a mistake, again, which is very easy to do, to catch that mistake. So that's why we're also going to show you how to use a calculator to do all of this. So let's do this last one, and then I'll show you how to use the graphing calculator. So we're going to take first row times the third column, and that's what's going to go here. 2 times negative 8, negative 16. 0 times 0 is 0. Negative 1 times 2, negative 2. 3 times negative 1, negative 3. We add it all together. These are all negative. There's negative 5, so that should be negative 21. And finally, we're going to take the second row times the last column, and that'll give us our very last spot. 1 times negative 8, negative 8. Negative 1 times 0 is 0. 2 times 2 is 4. Negative 2 times negative 1 is positive 2. So we get 6 and negative 8. That's negative 2. Negative 2. Now let's take a look, and hopefully I can pull it up fairly quickly. Get my graphing calculator, show you how we can do this with the graphing calculator. Those, let me first, we're going to have to enter these two matrices. So let me show you how to clear a matrix. So we go second, memory. And if you go down to memory management or delete, what we're going to do is do some deleting. We want to delete matrices. And I don't know what these ones are, so I'm just going to clear them. Well, no, I can't clear them. You hit delete. Second, memory manager. Number 5 for matrix, jump down there, and then I'm going to delete, delete, delete. Okay. Second matrix, I'm going to edit. I'm going to put in my A matrix, which is a 2 by 4. Put in a 2 by 4 matrix. I'm going to enter it in as a 2, a 0, a negative 1, a 3. second row, a 1, a -1, a 2, a -2. I'm going to encourage you to do both of these. Learn both how to use the calculating tool and how to do it by hand so you have something you can check on. It's, to me, it's almost just as easy to make a copy error when I'm putting in a matrix as it is to make a calculation error as I go through these things. I need to put the second matrix in, matrix B, we'll call it. Edit matrix B, and that is a 4 by 3. 4 by 3. And we will put these in 1, and this one goes across the top. 8, so we do sort of rows first. 0, 5, 2, and -2, 8, -1. Again, we do a check to make sure everything is entered correctly. And then I'm going to quit, second quit, get back out here. What we're going to do is we're just going to multiply these two matrices. So I'm going to pull up matrix A under names, and I'm just going to hit enter. So that gives me matrix A. I'm going to hit the multiply sign, and I'm going to come back and pull up matrix B by its name. So I've got now A times B. When I hit enter, I get my answer, which looks pretty good because I think that's what we ended up with, right? 4, 21, -21, 4, -5, -2. So we validated that we got everything entered in correctly. We did the multiplication correctly as well. So we can use this both. Okay, so be able to do both of these. You don't have the TI-84 calculator. Casio does have a feature for a matrix as well, and I'd be happy to help you with that. Step back. The other screen, and let's continue. Okay. So when we start talking about square matrices, of course, there are many different sizes: 1 by 1, 2 by 2, 3 by 3. And the identity matrix, well, let's just see what that is. Should that be all ones, or, well, we find out that an identity matrix, what we want is when we multiply by anything, that we get the same matrix. That doesn't change anything. What we're going to find out is that there are ones along the main diagonal and zeros everywhere else. It doesn't matter its size, we're going to get 1, 1, 1, 1 down the diagonal, zeros everywhere else. So a bunch of zeros over here. So these are all zeros. So let's just look at some examples of some identity matrices here. 1 by 1 to a 4 by 4. Again, the 4 by 4, the diagonals are all ones and zeros everywhere else. This we're going to use in the next setting to actually solve equations, systems of equations. So we start with the matrix and we get it to look like the identity matrix, and we're going to find it gives us the answers we're looking for. Okay. The properties of an identity matrix is when we multiply any matrix, such as A, times the identity matrix, we get back what we started. And you could verify here. Again, you couldn't do this with your calculator because it doesn't work well with letters. If we had numbers, we could see that this would happen. But you could just kind of see this one. When you take the row times this column, you're going to get A here. You're going to get 0 and 0 from this. So A plus 0, that's how we got that one. The next row, we would take this row times the same first column. And again, we get D times 1, that's D. E and F get multiplied by 0, so those are zeros. So we would get D there. And finally, we would take row 3 times the column 1, G times 1, that's G. These two H and I get multiplied by 0, so those are zeros, right? And you could follow through. The same thing's going to happen with your middle term. When you multiply ABC, this row, times the second column, B will be the only thing that's left, and that's what goes there. So um, walk through and you'll see how that works. The nice thing with the identity matrix is you can actually multiply on either side, and it will, which isn't usually true, right? The order of multiplication is generally important, except when we have the identity matrix, okay? Either on the left side or the right side, which is kind of nice. And we'll be using this in a little bit later as we solve some other things, okay? And again, we always need to check the dimensions of a matrix as we go through and multiply. So here are just some quick and easy properties. If we multiply a matrix times the scalar 1, that's a number 1, not a matrix, just we get the matrix back. We multiply by 0, everything turns to 0. We have an associative law of multiplication. So again, we've got to keep the same order, but we can group. We can either multiply BC first and then A, or we can multiply AB and then C if they can be multiplied. Same thing, there's an associative law for scalars. So again, we can do this in kind of a different grouping. And if we're going to multiply by two scalars, say C and D, these are just numbers, that works as well. We looked at this identity. If we multiply by the identity matrix, we get back to where we started. And again, we can multiply either on the right side or the left side, and we get the same answer. There is a distributive law for matrices, so I can add the two matrices and then multiply, or I can distribute. I can do the multiplication first and then add, and I would get the same answer. And there's a distributive law basically from both sides. And there is a multiplication by a zero matrix, we get 0. And the zero matrix is not the identity matrix, it's just a matrix with all zeros. Okay. The one that's missing is a commutative property. You do not see matrix A times B is the same thing as matrix B times A, because in general it's not. Okay. In fact, they're going to hit that right here. We don't see that because that in general does not hold. Now, you could probably find some cases, you could, where that is true, but in general it's not true. So we're going to take a little bit more about transpositions and see how those work. There's a special property that we get. Remember, a transposition is taking the rows of one matrix and turning them into the columns of another. That's a transpose. So, row 1 becomes column 1. Row 1 going down, and this is row 2, which is now column 2. Okay. So we get this property that if we add two matrices and take its transpose, it's the same thing as taking the transpose of both matrices and then adding. That sort of follows. This one we can either multiply by a scalar and then transpose, or we can transpose it and multiply by that scalar. Again, the scalar is just a number. So this will also prove true. You can try it out. This is what we're going to take a look at. And again, we can do it by proving it to ourselves by trying it out with the calculator. And we might do that. So we could take A times B and then take its transpose. But look at here, if we do the transpose first, then we have to take B times A. So the order of the multiplication changes. It's just a change in order. And one way to see that this is true is if we multiply the matrices first. So this is A and this is B. We take its transpose afterwards. So we do the multiplication first, we got here. Then we transpose it. So negative 2, 10 is going to become the row, or if you want the row becomes a column, right? Negative 2, 1 becomes negative 2, 1 in this fashion. So we see the transpose here. And then we take the transposes first, but notice this is the transpose of B, and this is the transpose of A. Then we multiply this way, right? Well, we take the transpose. Well, this is, sorry, let me back up. This is not the transpose. This is just B, and this is A. We're not multiplying yet. We're going to take their transpose. This is the transpose of B. This is a transpose of A over here. When we multiply, we get the same thing. So these two are equal. So what we've just done in a way is prove that A times B transpose gives us the same result as B transpose A transpose. Now we haven't proved it because we haven't done it for everything, but what we'll also do is we'll do one more. What if we didn't switch the order? What if we kept it A, B, which we did here? And so we take the transpose first, and then we try multiplying. We don't get the same answer. So it just kind of shows that if we don't change the order, we don't get the correct answer. Okay. And again, it's just we'll be pulling up this property a little bit later. That A times B transpose is equal to B transpose A transpose. Properties of the transpose. We'll work at those later. One of the issues one of the reasons we'll be working with them is we will start looking at a matrix sort of as a system of equations, right? So we're going our system of equations more as an equation. So we'll come up with this equation, a linear equation, AX equals B, where A is a matrix and the X matrix is the variables. What we're going to look at is this is basically saying column 1 is all your X variables, column 2 is your Y variables, and column 3 is your Z variables. And then these are, thinking of them as equations, this becomes, the B matrix becomes sort of like the answer matrix. So what we get is the first equation, if we were to sort of translate from here, is going to be 1x minus 2y plus 3z equals 3. So notice I'm getting those right from that first row. And when we actually do the multiplication, this is x, y, and z. Second equation is going to be 2x plus 0y, which disappears. It won't show up. We'll see it. They've got it later. Minus 1z equals negative 1. So these are coefficients of the variables, and then these are kind of what the equation is equal to. And then we get negative 3x plus 1y plus 1z equals 0. We've got this system of equations, and there's going to be times when we'll use this sort of a setup as an equation to solve it. We're also going to look at other ways of solving this system of equations, but this is the starting point. So here it is, it lays it out in more detail. The left-hand side, if you were to multiply all that out, what you get is you get these matrix, you get those equations. And notice they're, rather than putting in 0y, they just leave it out, but I like to leave the spacing. So in the middle, they just left out the y. That's fine. They don't have 1z, but I did, or negative 1z. So they put all those in. And then it's equal to this. So these are sort of what the answers are equal to. So if we were to translate it all the way out, it's 3 equations, 3 unknowns. And if we're generally able to solve an equation like this for what x, y, and z are. Okay, so just a conceptual, this is what we're moving towards. So it's a system of equations. We're using matrix. We're using just the coefficients. And what we're going to see is that we are going to work with a matrix with just the numbers, the coefficients, and not have the variables there. And in some ways, uh, it'll be easier to work with. Also, it allows us to solve these using uh, graphing calculators that we have with the matrix feature or other computer programs. Okay, so part of this is just to get practice. How do we express this as a system, sort of as a linear equation? Where we're going to take the coefficients of 2 and 1. This is going to be the matrix A. Down here we get coefficients of 4 and -1. We're going to multiply that times the variable matrix, which are x and y. We just call that big X. And then all that is going to be equal to the, I guess I call it the answer matrix of 3 and -1. Okay, that's how we do that one. And this is the very last slide. So for this lesson, that's all we have. We're going to actually start applying this sort of solution. We're also going to, the next section we're going to look at augmented matrix, where we basically represent this sort of same thing with just a single matrix. We'll just kind of leave this, so we kind of leave this off. We put these two together as a single matrix, and then we're going to solve that system. All right, thank you.